So, in the packet that I gave you, we're going to skip the opening exercise. We're going to come back to that on Wednesday. All right? What I want you to do is think about exercise 1 through 13. We're going to start off by reading. The owner of Dizzy Lizzie's Amusement Park are studying the wait time at their most popular roller coaster. The table below shows the number of people standing in line for the roller coaster, T number of hours after the roller coaster opens. So, right when the roller coaster opens, there's nobody in line. 1 hour after the roller coaster opens, there's 75 people in line. 2 hours after the roller coaster opens, there's 225, and so on. So does everybody understand the general gist of the graph, or of the table? Okay, now, Jalen made a scatter plot and decided that a cubic function should be used to model the data. Why did he choose a cubic function? Well, let's see about that. First of all, let's see now. Here's the dots. So everything that's in the table here, he's got dots here. So he put plots on his graph for every single dot that or every single point that he has on the table. Now, he decided that a cubic would be his model, the function he decided that a cubic function should model the data. All right? Now, we're going to go, do you think that a cubic is a good model for that data? In order to talk about this in greater detail, let's go back to the graph. Do you think a cubic model is a good model for this? What's that? A cubic model. So, remember, a cubic model looks like this. Let's do P of T equals. And this isn't the cubic function, but I'll just give an example. So maybe it's T minus 3 times T minus 15 times T minus 37. Maybe that's the cubic function. Okay? But is a cubic the only thing that would be a good use for this model? Or a good model for this? Who thinks there's something else that they could do? What do you think, Liv?
Well, I'm not saying that I'm going to do anything else to it because I already know what to do, but I feel like depending on the situation, that the model, I guess you would say, or the function, the curve.
Yes.
I guess that it's a yes and no kind of thing because maybe one day, yes, the curve might fit it better, but another day it might be more sporadic in between the different dots.
No, that's a really good point. That's a really good point. But, well, what Liv is saying is, well, we did this on Monday, let's say. Oh. Just pretend like we did this on Monday. Am I going to get the same thing on Tuesday?
There's no information that says that on there. So
no, there's not. There's not.
Yeah, come on.
We're thinking about things here. We're not just doing. You guys are really good at doing stuff. You know what I mean? If I tell you to go do something, you do it. But if I ask you to think about something, what do I hear when I ask you to think about something?
How did you think
It's hard for us, right? Because we've been trained to do stuff, but not think about stuff. And we're trying to teach you how to think about these things. Now, let me ask you this. How many times can a cubic cross the x-axis? What do you think, Josh? 3 times. 3 times. Does it have to cross 3 times? It doesn't have to, but it can cross 3 times. Now, these are real points right here. I'll put these in red. These guys right here are all real points that he graphed from his data that he took on the table. But what does the blue line here, the one that Jalen drew on this blue line is what results from the cubic function. Right? Does this part help us at all? Let me ask you this. If we did another data point at 13 hours and 14 hours, what would my cubic function get me? It'd give me a line with negative number of people in it, right? Okay. What information would Busy Lizzies be interested in learning about from this graph? What information would they be interested in? I wish they had that. What do you think they'd be interested in? What information would the owner of the amusement park be interested in? Think about this as a customer. Who's been to an amusement park before? 3 people.
I've been back there.
Okay, that's an amusement park.
I've been there.
All right, do you want to hit... What's America?
No.
Do you want to hit the line at this time?
No. Right.
Okay.
The other guy.
So, now, how does this affect the owners of the amusement park? If I make my people wait, people are waiting longer at this time, right?
They don't want to go at that time.
They don't want to go at that time. So this might impact a company's bottom line, right, Garrett? I might not make as much money because I'm making my poor customers wait all this time. So, what information would they be interested in? So what? So what? So I make my people wait.
Make more roller coasters.
That might make them a bigger roller coaster. How much does it cost to make a roller coaster?
Oh, wow.
Right? Anybody want all the information before they jump into that type of investment, right? All right, so estimate the time. Check this out. Estimate the time that the roller coaster's line is the longest. At what time is the roller coaster line the longest, Jordan? At the top point, right? So I'll put that in green, right here. At that point, the roller coaster line, at least the model says, at this point the line will be the longest. And that point is how many hours? I can't tell. That'd be just under 2 hours? No. No, it goes by each line. Okay, so that's 5 hours. at 5 hours. Okay? Estimate the number of people at that time. Let's go back to the graph. How many people are at the ride at that time? 250. 175 divided by 1, 2, 3, 4, 5. What's 175 divided by, or 125 divided by 5 is 25. So this is, right here is 350. So what? I would say that's probably 360, 365, thereabouts. Approximately. All right. Now, number 5, it asks us to estimate the t-intercepts of the function used to model this data. What do they mean? What do they mean by that, Caleb? Estimate the t-intercepts. What in the wide world of sports does that mean? Crossing what? Intersecting the t-axis. Do you agree with that, Jasmine? So, at what points does this function cross the t-axis? Well, it crosses here, right? And is that an estimate?
Wait, what? No.
The t-axis. The axis that's labeled t. Is that an estimate, though? Why not? I got a data point right there, right? So that's not an estimate. That's a hard point. How about this guy, though?
Like 13.
This is an estimate.
Yes. Like 13.
13?
13.
10, 11, 12. I got 12.
Holy man.
Maybe 12 and a half.
I'll say 12.3.
12.3?
Yeah.
You down with that?
Yeah.
Okay, what about this guy over here? What's that? That's another intercept, isn't that? Yes, Jeff. 33? 33. Yeah, okay. So 0, 12.3, and 33. So 0 hours, 12.3 hours, and 33 hours. Now, use the t-intercepts to write a formula for the function. This sounds a lot like I got zeros, and now I write my polynomial function, right? So, t equals 0. What's the factor that would make t equals 0 a solution? 0. Just t, right? T would be my factor. What's the factor that would make this a solution? Nice and loud, Jasmine. So, times t minus 12.3. And then one last one. What do you think that last one would be, Ethan?
There would be t minus 33.
T minus 33. And that's, but we're not just interested in the zeros, we're interested in the whole kit and caboodle. We're going to put that as t is a function of t. So the people in line as a function of time. Alright? And then it says, use the relative maximum to find the leading coefficient of F. Explain the reasoning. So, here's what we're going to do, okay? All these things tell me is where that function crosses the t-axis, right? But it does not tell me, it doesn't tell me how high this goes. So what we're going to do is we're going to use the point we found there, and we're going to use those zeros to come up with a new function. Here's how we do that. So, I'm going to put a coefficient, I'm going to call it A, in front of that whole thing. This A will tell me how high that thing goes. So now I got P of, remember, at 5 hours, we had 365 people. So P of 5 equals 365, which equals A times, now I put my T's in, times 5 times 5 minus 12.5 times, or no, not 12.5, 12.3. 12.3, and then 5 minus 33. So I'm basically putting in an answer here, and then I'm putting in my times, and I'm going to solve for A. So what is 5 minus 12.3? That's negative 7.3. And 5 minus 33 is negative 28. Am I right? And then A times 5. This all equals 365. So now, how do I solve for A? I'm multiplying, so what's the opposite of multiplying, Josh? So what do I divide by?
Oh, 5 times.
I divide by 5?
Times as
yeah.
You could do that.
Yeah, so I'm going to divide by 5 times 7.3 times, yep, negative 7.3 times negative 28. If I divide that, this side by this, it cancels out, but I should also divide the other side by that, right? Except I'm lazy and I don't want to write all this stuff down on the other side. What should I write down on the other side? Who's got a new calculator that they just got that they need to learn how to use? You already got it, Kate?
No.
Oh, you don't have the calculator, huh? 25 times 5 is 125. 125 plus 15 is 140. 140 times 7. What's 140 times 7? What is it? Go for it. 1,022. 5 times 7.3 times 28.
Yeah.
Okay.
Why does negative 7.3 negative 28?
Okay. Yeah. Okay. So what is 365 divided by 1022? Because on this side, all this stuff goes away. I'm left with A, right? So A equals this business. So what is A? Give me a number, somebody. Give me a correct number.
Is
Very.
It's going to be a decimal, yeah.
0.357142857.
Yeah, so there would be your A value. So then, now,
That's fine. That's fine.
that's just the number that I multiply this whole thing by.
And
That's what gives me the right height for my function. Now, I riddle you this. Let's look back to the graph. We'll come back to it in a second, Andrew. But I want to think about this. What is a reasonable domain for this function? Who remembers what a domain is? Okay, write this down in your notes. Domain. Domain is the set of all inputs into a function. That is what a domain is. The set of all inputs into a function. That is your domain. Okay? What do you think a reasonable domain for this model would be? What doesn't make sense? Do these numbers down here make sense? Why not? We're not in Osceola, right? That was a bad joke. Bad joke. Yeah, you're right? It doesn't make sense to have negative number of people in line. So, what would be my domain? How can I fix it to where I don't have a negative number of people? I can just say, well, look, I'm only interested in values between 0 and 12.3. I'm just interested in stuff between 0 and 12.3. So my domain, to answer this question, my domain would be T is between 0 and 12.3. And the reason is because I don't want negative people. I'll put that quotation marks in my model. Now, use your calculator. Remember, t as a function of t equals 0.357 t times t minus 12.3 times t minus 33. Now, use your calculator to calculate the number of people in line 10 hours after the park opens. So I want to calculate P when t equals 10. Caleb, Josh? So everywhere I see a t, I'm replacing with what? With 10, right? 0.357 times 10 times the quantity, 10 minus 12.3 times the quantity, 10 minus 33. And now I've plugged in, now I chug. So this is 3.57 times negative 2.3 times negative 22. That should make our calculations easier.
We got this then.
No, I didn't, because I multiplied this times this already.
Oh.
What's that, Sophia? Oh, 23, thank you. Anybody get a number for that? All right. We will have on the back of that packet is an exit ticket. That's what we'll be doing in class tomorrow with the substitute. Have a good day. We'll see you Wednesday.